Hello and welcome. If you are settling in for the evening, finding your position, letting the quiet gather, letting the weight of the day begin to lift, then you have come to exactly the right place. This is the Science Channel for Sleep, and tonight we are going somewhere vast. We are going to the edge of human understanding, to the questions that the most careful and talented scientists alive are working on right now, and that remain, despite decades of effort, genuinely open. Tonight, we are exploring the greatest mysteries of space that scientists still cannot explain. Before we begin, if you enjoy this kind of calm, unhurried journey through the deep questions of science, if this is the kind of content you like to fall asleep to or rest quietly alongside, it would mean a great deal if you took a moment to like this video and subscribe to the channel. It helps more than you might expect, and it helps this channel continue making exactly this kind of content. And if you feel like leaving a comment, we would love to know where in the world you are listening from tonight and what time it is there. It is always interesting discovering where listeners are tuning in from around the world. Now, let us begin with a number, 5%. That is the fraction of the universe that is made of anything we can see, touch, detect, or understand. Stars, planets, gas, dust, you, everything you have ever encountered or will ever encounter. All of it amounts to approximately 5% of what is actually out there. The other 95% is invisible, undetected, and, despite decades of searching, still completely unknown in its fundamental nature. The observable universe extends approximately 46 billion light years in every direction from Earth. Within that vast sphere, there are an estimated 2 trillion galaxies. The universe is approximately 13.8 billion years old. And across all of that space, across all of that time, the same laws of physics appear to apply everywhere we have been able to test them. These are extraordinary things to know, and we know them because of centuries of careful observation and mathematical reasoning, one of the most sustained and productive intellectual endeavors in human history. And yet, the two foundational theories of modern physics, general relativity, which describes gravity and the large-scale structure of space-time, and quantum mechanics, which describes the behavior of matter at the smallest scales, are mathematically incompatible with each other. The nature of dark matter and dark energy, together constituting 95% of the universe, is completely unknown. We do not know what caused the Big Bang, or what, if anything, came before it. We do not know why the universe contains matter rather than nothing. We do not know whether we are alone. Tonight, we are going to sit with these questions, slowly, carefully, without any pretense that they will be resolved tonight, or perhaps in any of our lifetimes. The purpose of tonight is not to arrive at answers, but to appreciate the questions, to understand what the mysteries are, why they are so deep, and what they tell us about how far human understanding has come and how far it has yet to go. Researchers believe that sitting with genuine uncertainty, with questions that resist easy resolution, is one of the more honest and rewarding things a curious mind can do. The universe's unanswered questions are not signs of science's failure. They are the frontier. They are where the most interesting work is being done. Let us begin with the largest mystery of all, the invisible universe that surrounds us on all sides. Look up at the night sky on a clear evening, and you will see stars, hundreds of them visible to the naked eye, thousands through binoculars, billions through a telescope. The sky seems full of light, full of matter, full of the familiar substance of the world. What you are seeing is approximately 5% of what is actually there. The universe is, in its overwhelming majority, made of things we cannot see, cannot detect directly, and do not understand. Two of these things have been given names: dark matter and dark energy, and together they constitute approximately 95% of everything. Understanding them is the central challenge of modern cosmology, and despite decades of effort, neither has been explained. Let us begin with dark matter. In 1933, a Swiss-American astronomer named Fritz Zwicky was studying the Coma Cluster, a collection of galaxies approximately 320 million light-years from Earth. He measured the velocities of individual galaxies within the cluster and found something puzzling. The galaxies were moving far too fast to be held together by the gravity of the visible matter, the stars and gas he could see. If the cluster contained only the matter he could observe, the galaxies should have long since flown apart. Something invisible was holding them together. Something with gravitational pull, but no detectable light. Zwicky called it dunkel materia, dark matter. His proposal was largely ignored. 40 years later, the astronomer Vera Rubin, working with Kent Ford, provided evidence so compelling that dark matter could no longer be set aside. Rubin was studying the rotation of individual galaxies, measuring how fast stars at different distances from the galactic center were orbiting. According to Newtonian gravity, stars far from the center, where visible matter is sparse, should orbit slowly, just as the outer planets of our solar system orbit the sun more slowly than the inner ones. Instead, Rubin found that stars at the outer edges of galaxies orbit at approximately the same speed as stars near the center. The rotation curve is flat rather than declining. The only way to explain this flatness is to assume that a vast halo of invisible matter surrounds each galaxy. Dark matter, extending far beyond the visible disk, its gravitational pull keeping the outer stars moving faster than visible matter alone could account for. Scientists have found dark matter's gravitational fingerprints everywhere they look. It bends light from distant galaxies through gravitational lensing. It shapes the large-scale structure of the universe, the cosmic web of filaments and voids. It was essential for the formation of galaxies themselves, providing the gravitational scaffolding around which visible matter accumulated. Without dark matter, galaxies, as we know them, likely would not exist. But what is dark matter? Researchers believe it is some form of particle or particles that do not interact with light and are only weakly interacting with ordinary matter. The leading candidates have included WIMPs, weakly interacting massive particles, axions, and sterile neutrinos. Experiments deep underground designed to detect the rare interactions of dark matter particles with ordinary matter have been running for decades. They have found nothing. The absence of detection has eliminated many candidates and constrained the properties of others, but dark matter itself remains undetected. Dark energy is, if possible, even more mysterious. In 1998, two independent teams of astronomers studying distant supernovae, using them as standard candles to measure cosmic distances, made a discovery that neither team expected. The distant supernovae were dimmer than they should have been. The universe was not just expanding, it was accelerating in its expansion. Something was driving the expansion faster and faster over time. That something was named dark energy. It constitutes approximately 68% of the universe's total mass energy content. Its nature is completely unknown. One possibility is that dark energy is what Einstein called the cosmological constant, a fixed energy density of empty space that does not change over time. Einstein originally introduced it to balance gravity and keep the universe static, then abandoned it when Hubble discovered the universe was expanding. It has since been revived as a possible description of dark energy. Another possibility is that dark energy changes over time, an evolving field sometimes called quintessence. If it strengthens over time, it could eventually overcome gravity, tearing apart galaxy clusters, then individual galaxies, then solar systems, then planets, then atoms, and finally space-time itself. A scenario called the Big Rip. The Euclid Space Telescope, launched in 2023, is designed to map the distribution of dark matter and measure dark energy's behavior across cosmic time, determining whether it is constant or evolving. Its observations over the coming years may tell us whether dark energy is Einstein's cosmological constant or something more dynamic. It turns out that even asking the right question about dark matter and dark energy requires physics we may not yet have. The standard cosmological model, which incorporates both, fits the observations very well, but it describes neither. It tells us how much of each there is and what they do. It does not tell us what they are. 95% of the universe, patient and invisible, waiting for an explanation that has not yet arrived. The mystery of what the universe is made of leads naturally to the question of where it came from. That is where we are going next. This is the picture that modern cosmology gives us of the earliest moments we can describe. A universe in a state of inconceivable temperature and pressure, expanding and cooling from its initial state into the cosmos we inhabit today. The Big Bang Theory describes this expansion with remarkable precision. It predicts the abundances of the lightest elements, hydrogen, helium, and lithium, produced in the first few minutes of the universe's existence. It predicts the existence of the cosmic microwave background radiation, the faint thermal afterglow of the early universe. And those predictions have been confirmed to extraordinary accuracy by observation. What the Big Bang Theory does not tell us is why. Why did the universe begin expanding? What caused the initial state of extreme heat and density? What, if anything, came before? These questions sit at the edge of what physics can currently address, and in some cases may require a fundamental rethinking of what physics is capable of saying. One misconception worth addressing gently: the Big Bang was not an explosion in the conventional sense. It was not a fireball erupting into pre-existing empty space. There was no center from which everything expanded. Space itself expanded, carrying matter and energy within it. Every point in the universe was, at the moment of the Big Bang, every other point in the universe. The expansion happened everywhere simultaneously, and there was nowhere outside it. The cosmic microwave background, the CMB, is our most direct window into the early universe. It is the light released approximately 380,000 years after the Big Bang, when the universe had cooled enough for electrons to combine with protons and form neutral hydrogen atoms. Before this moment, the universe was a dense, opaque plasma. Light could not travel freely. After it, the universe became transparent, and the light released at that moment has been traveling through space ever since, cooling and redshifting, until today it fills all of space as a faint background of microwave radiation at approximately 2.7 degrees above absolute zero. The CMB was discovered accidentally in 1965 by Arno Penzias and Robert Wilson, two radio engineers at Bell Labs in New Jersey, who were testing a new antenna and found a persistent background noise they could not eliminate. They initially suspected pigeon droppings in the antenna horn. The noise turned out to be the afterglow of the Big Bang, a signal predicted theoretically nearly 2 decades earlier by George Gamow and his colleagues, and now one of the most precisely measured phenomena in all of science. But the CMB revealed something puzzling. Its temperature is extraordinarily uniform, the same in all directions to 1 part in 100,000. This might seem unremarkable, but it poses a deep problem. The CMB represents the universe at a time when different regions of the sky were so far apart that, given the age of the universe at that point and the speed of light, they could never have communicated with each other. Regions that were causally disconnected, that had no way to exchange energy or information, somehow had exactly the same temperature. This is called the horizon problem. There is also the flatness problem. The universe is geometrically flat, meaning parallel lines remain parallel across cosmic distances to an extraordinary degree of precision. In the early universe, any slight deviation from perfect flatness would have grown over time into enormous curvature. For the universe to be as flat as we observe it today, the initial conditions must have been tuned to extraordinary precision. In 1980, a physicist named Alan Guth proposed a solution to both problems: cosmic inflation. Inflation posits that in the first tiny fraction of a second after the Big Bang, perhaps from 10 to the negative 36 seconds to 10 to the negative 32 seconds, the universe underwent an extraordinarily rapid exponential expansion, growing by a factor of at least 10 to the 26. This expansion would have taken any region of the universe that was initially in causal contact and stretched it far beyond the observable horizon, explaining why different parts of the CMB have the same temperature. They were once in contact. Inflation also stretched any initial curvature flat, explaining the flatness problem. Inflation also provides a mechanism for the origin of all structure in the universe. During inflation, tiny quantum fluctuations, the microscopic random variations predicted by quantum mechanics, were stretched to macroscopic scales. These fluctuations became the density variations that eventually, under gravity, grew into the cosmic web of filaments and voids, the galaxy clusters, and ultimately the stars and planets we see today. The quantum fluctuations of the early universe became everything, but inflation itself raises questions it cannot answer. What caused inflation? What is the inflaton, the scalar field thought to drive the rapid expansion? What caused inflation to stop? The answers to these questions are not known. Various inflationary models make different predictions about the details of the CMB's polarization, and future observations may help distinguish between them. But the fundamental mechanism of inflation remains an open question. And then there is the deepest question of all. The Big Bang describes the universe's evolution from an initial state, but it does not describe the origin of that initial state. What came before the Big Bang? The question may have no physical answer. If time itself began at the Big Bang, the concept of before is meaningless. Or it may require new physics, a theory of quantum gravity capable of describing the singularity at the universe's beginning that does not yet exist. Why does anything exist rather than nothing? This question sits at the boundary between physics and philosophy, between science and something older. It is the deepest question the universe invites us to ask, and it remains, as it has always been, open. What the universe will eventually become is, in some ways, an easier question, though not an easy one. That is where we are going next. The universe has a future, a very long one by any ordinary standard, but a future that, according to our best current understanding, ends in one of several possible ways, each more remote than anything human intuition can easily hold. The nature of that ending depends, more than anything else, on the nature of dark energy, which, as we have seen, we do not yet understand. What we do know is that the universe is expanding, and that its expansion is accelerating. Galaxies are receding from one another, and the farther away they are, the faster they recede. Beyond a certain distance, a boundary sometimes called the Hubble radius, galaxies are receding from us faster than the speed of light. This does not violate special relativity, because it is not the galaxies themselves moving through space at superluminal speeds. It is space itself expanding between us and them, but the effect is the same. Light from those galaxies will never reach us. In approximately 2 trillion years, a span of time so vast it makes the current age of the universe seem brief, the expansion of the universe will have moved all galaxies outside our local group beyond the observable horizon. Future astronomers in a hypothetical galaxy of that era would look out and see nothing. No external galaxies, no evidence of the cosmic web, no hint that anything exists beyond the small island of stars they inhabit. They would have no way to discover what we know, that the universe contains 2 trillion galaxies, that it is expanding, that it began in a hot, dense state 13.8 billion years ago. The information needed to reconstruct modern cosmology will simply be gone, carried over the horizon by the expansion of space. Interestingly, this means that the moment in cosmic history we happen to occupy is a privileged one. We live at a time when the evidence for the Big Bang, the CMB, the large-scale structure of galaxies, the abundance of light elements, is still observable. In the far future, those clues will be gone. We are fortunate, if fortunate is the right word, to exist in the era when the universe is still legible. The most likely scenario for the ultimate fate of the universe, given current observations, is what physicists call the Big Freeze, or heat death. In this scenario, the universe continues expanding and cooling indefinitely. Stars form from gas and dust, shine for millions or billions of years, and then exhaust their fuel, becoming white dwarfs, neutron stars, or black holes. Over trillions of years, white dwarfs cool to black dwarfs, dark cold embers. Black holes slowly evaporate through Hawking radiation over incomprehensibly long timescales, the last black holes evaporating in perhaps 10 to the power of 100 years. Eventually, the universe approaches a state of maximum entropy, a condition in which energy is distributed as uniformly as possible across space and no thermodynamic gradients remain. No further work can be extracted from any physical process. No stars can shine, no chemistry can occur, no structure of any kind can form or persist. The universe reaches its final equilibrium, cold, dark, and still, essentially forever. This is the heat death, and according to current understanding of dark energy, it is the most likely ultimate fate. But dark energy might not remain constant. If dark energy strengthens over time, a possibility that current observations cannot rule out, it could eventually overcome not just the gravity holding galaxy clusters together, but the gravity holding individual galaxies together, then solar systems, then planets, then the electromagnetic forces holding molecules together, then the nuclear forces holding atomic nuclei together, and ultimately, space-time itself. In this scenario, called the Big Rip, the universe is literally torn apart on every scale, from the largest structures down to subatomic particles. The time remaining to the Big Rip would depend on how rapidly dark energy strengthens. If dark energy does strengthen significantly, the Big Rip might occur in tens of billions of years. Not the unimaginable timescales of the heat death, but still enormously distant by any human measure. These two scenarios bracket the range of likely possibilities. A third, the Big Crunch, in which gravity eventually reverses the expansion and the universe collapses back on itself, is considered very unlikely given the observed accelerating expansion, but cannot be entirely ruled out. The arrow of time is intimately related to these scenarios. The second law of thermodynamics states that entropy, the measure of disorder in a system, increases in closed systems over time. The universe as a whole moves from lower entropy to higher entropy, from order to disorder, from a hot, dense, structured state at the Big Bang toward the cold, uniform, featureless state of the heat death. But here is one of physics' deepest puzzles. The fundamental laws of physics, the equations of classical mechanics, quantum mechanics, and general relativity, are time-symmetric. They work equally well in both directions of time. There is no law that distinguishes the past from the future, and yet we experience time as flowing in only one direction, from past to future, from cause to effect, from memory toward anticipation. Why does time have a direction? Why is there an arrow of time pointing from the Big Bang toward the heat death? Physics does not currently have a satisfying answer. One reason may be the extraordinarily low entropy of the early universe. The fact that the Big Bang began in an unusually ordered state. But why the early universe was in such a low entropy state is itself unexplained. time itself, what it is, whether it had a beginning and will have an end, why it appears to flow in only one direction, remains one of the deepest unresolved questions in all of physics. And nowhere does the mystery of time become more acute than in the study of objects where time, as we understand it, may cease to have ordinary meaning. Those objects are where we are going next. In December of 1915, Albert Einstein published the final form of his general theory of relativity. The theory described gravity not as a force acting at a distance, as Newton had, but as the curvature of space-time caused by mass and energy. Mass tells space-time how to curve, and curved space-time tells mass how to move. Within weeks, a German physicist named Karl Schwarzschild, serving on the Russian front in World War I, found an exact solution to Einstein's equations describing the space-time geometry around a spherically symmetric mass. When Schwarzschild sent his solution to Einstein, Einstein wrote back that he had not expected an exact solution to be found so quickly, and that it was a very interesting mathematical result. What Schwarzschild's solution described, though neither man fully appreciated it at the time, was a black hole. A black hole is a region of space-time where gravity is so strong that nothing, not matter, not radiation, not light itself, can escape from within a boundary called the event horizon. The event horizon is not a physical surface. It is a mathematical boundary, the point of no return, defined by the condition that escape velocity exceeds the speed of light. Cross it, and no matter how powerful your engines or how fast your speed, you cannot return to the universe outside. The radius of the event horizon is called the Schwarzschild radius, and it is proportional to the mass of the black hole. For the Sun, the Schwarzschild radius would be approximately 3 kilometers, meaning that if you compress the entire mass of the Sun into a sphere 3 kilometers in radius, it would become a black hole. For the Earth, the Schwarzschild radius is approximately 9 millimeters, the size of a marble. In practice, black holes form from the collapse of massive stars. When a star several times more massive than the Sun exhausts its nuclear fuel, its core collapses under gravity. If the core is massive enough, greater than approximately 3 solar masses, the collapse cannot be halted by any known force, and the core collapses to a black hole. But the most extraordinary black holes are not the stellar mass ones formed from collapsing stars. They are the supermassive black holes that sit at the centers of almost every large galaxy, objects containing millions to billions of times the mass of the Sun. The supermassive black hole at the center of our own Milky Way, Sagittarius, a star, has a mass of approximately 4 million solar masses. In 2022, the Event Horizon Telescope collaboration released the first image of it, a blurry orange ring of light surrounding a dark shadow, produced by photons orbiting just outside the event horizon, before escaping to reach our telescopes. The image was produced by coordinating observations from radio telescopes distributed across the entire Earth, effectively creating a telescope the size of the planet. The first Event Horizon Telescope image, released in 2019, showed the black hole at the center of galaxy M87, 6.5 billion times the mass of the Sun, one of the largest black holes ever measured. These images confirmed predictions that had stood for over a century, but they also deepened one of the most important unsolved problems in physics. How did supermassive black holes form? Observations of the early universe, less than 1 billion years after the Big Bang, have revealed quasars, brilliantly luminous objects powered by supermassive black holes, consuming matter at prodigious rates. These early quasars harbor black holes of billions of solar masses. But the standard model of black hole growth, steady accumulation of mass through accretion, cannot grow a black hole from stellar collapse to billions of solar masses in less than 1 billion years. The early supermassive black holes grew much faster than current models can explain. At the center of every black hole, beneath the event horizon, the mathematics of general relativity predicts a singularity, a point of infinite density where the curvature of space-time becomes infinite. Most physicists believe this mathematical infinity indicates not a physical reality, but a breakdown of the theory. General relativity, extraordinarily accurate in every other context, simply ceases to be applicable at the singularity. What actually happens at the center of a black hole requires a theory of quantum gravity, a framework uniting general relativity with quantum mechanics that does not yet exist. The information paradox adds another layer of mystery. Quantum mechanics holds that information, the precise specification of a physical system's state, cannot be destroyed. If you burn a book, the information in the book is in principle recoverable from the ashes and the heat and the light and the particles. However, impractically, information is conserved. Stephen Hawking showed in 1974 that black holes should slowly emit thermal radiation, now called Hawking radiation, through quantum effects near the event horizon. Over extraordinarily long timescales, a black hole loses mass and eventually evaporates completely. But the Hawking radiation is purely thermal. It carries no information about what fell in. If the black hole evaporates completely, the information about everything that ever fell into it appears to be lost, destroyed. But quantum mechanics says information cannot be destroyed. Something has to give. The holographic principle, proposed by Gerard 't Hooft and Leonard Susskind, offers one possible resolution. It suggests that all the information contained within a volume of space can be encoded on its boundary surface, like a 3-dimensional image encoded on a 2-dimensional hologram. If this is correct, the information of matter falling into a black hole might be encoded on the event horizon and returned in some scrambled form through the Hawking radiation. Whether the holographic principle resolves the information paradox and what it implies about the fundamental nature of space-time remains one of the central open questions in theoretical physics. The mysteries of black holes, the singularity, the information paradox, the rapid formation of early supermassive black holes, all point toward physics we do not yet have. And those mysteries connect to another question that is, in a sense, the most personal mystery of all. The question of why we exist. That is where we are going next. Why does the universe contain anything at all? Not anything at all in the philosophical sense, but anything in a very specific physical sense. According to the standard model of particle physics, matter and antimatter are produced in equal quantities in high-energy processes. For every electron, an anti-electron, or positron. For every proton, an antiproton. matter and its mirror image created in perfect pairs. In the earliest moments of the Big Bang, the universe was an extraordinarily hot and energetic place, conditions under which matter and antimatter were being produced and annihilated continuously. When two particles of matter and antimatter meet, they annihilate, converting their mass entirely into energy, into photons of radiation. If matter and antimatter were created in precisely equal quantities, they would have annihilated completely, leaving a universe containing nothing but radiation. No stars, no planets, no atoms of any kind, no us. And yet here we are, in a universe filled with matter. Something happened in the early universe to break the perfect symmetry between matter and antimatter. For every billion antiparticles, there were approximately 1,000,000,001 matter particles. That one extra particle in a billion, surviving the great annihilation, became everything. Every star in every galaxy, every atom in every living thing, the ground beneath buildings, and the water in oceans, and the carbon in every strand of DNA. We are made of the survivors. The process that created this asymmetry is called baryogenesis, and it is not explained by known physics. In 1967, the Soviet physicist Andrei Sakharov identified 3 conditions that any process producing a matter-antimatter asymmetry must satisfy. First, it must violate baryon number, the quantity that counts the difference between particles and antiparticles must change. Second, it must violate charge conjugation symmetry and charge parity symmetry. The laws of physics must behave differently for matter and antimatter. Third, it must occur in conditions that are not in thermal equilibrium. Otherwise, any asymmetry produced would be immediately erased. The standard model of particle physics satisfies all 3 Sakharov conditions, but it satisfies them by a far too small a margin to produce the asymmetry we observe. The matter-antimatter asymmetry, predicted by the standard model, is orders of magnitude smaller than what actually exists. Something beyond the standard model must have operated in the early universe. Some process involving new particles or new forces that enhance the asymmetry to the level required for a matter-filled universe. What that process was is not known. The strong CP problem adds a related puzzle. Quantum chromodynamics, the theory of the strong nuclear force that binds quarks into protons and neutrons, has no theoretical reason not to violate charge parity symmetry. Yet experiments show that it does not, to extraordinary precision. Why the strong force respects CP symmetry when it has no obvious reason to do so is called the strong CP problem. One proposed solution is an undiscovered particle called the axion. The axion was proposed in 1977 by Roberto Peccei and Helen Quinn as a mechanism that dynamically drives the strong CP violation to 0. The axion's interactions naturally suppress the CP violating term in the strong force equations. The axion is extraordinarily light and barely interacts with ordinary matter. It has not been detected, but it is also one of the leading candidates for dark matter, a particle that, if it exists, would simultaneously solve 2 of physics' deepest mysteries. Experiments around the world are searching for axions. using resonant cavities in strong magnetic fields to attempt to convert axions into detectable photons. So far, no signal. Interestingly, the matter-antimatter asymmetry is also connected to the question of why the universe exists in a form compatible with life. If the asymmetry had been slightly different, if slightly fewer matter particles had survived relative to antiparticles, or if the asymmetry had been much larger, the universe would be profoundly different. The existence of matter at all is contingent on a physical process that physics cannot yet explain. The profound implication is this: our existence depends on a cosmic asymmetry whose cause is unknown. The fact that you are here, that any matter exists, is a consequence of a process that happened in the first fractions of a second of the universe's life, that current physics cannot account for, and that produced the 1 in a billion excess that became everything. It is a remarkable thought to carry into sleep. But there are other mysteries of a different character, mysteries not of origin, but of signal. The universe sends messages, and some of them we cannot read. That is where we are going next. On a clear night, if you were to tune a radio receiver to the right frequency and listen to the sky, you would hear a variety of sounds. The hiss of thermal radiation from distant objects, the regular pulses of pulsars, the slow drift of signals from known sources. The radio universe is busy and varied, and once you learn to interpret it, largely familiar. But occasionally, without warning, the radio sky produces something else entirely. A fast radio burst is a brief, intense pulse of radio waves arriving from cosmological distances, from sources billions of light years away. Each burst lasts only a few milliseconds, a fraction of a second, and in that brief time, it releases as much energy as the sun emits over the course of thousands of years. The energy of thousands of years of stellar output, compressed into a pulse lasting less than the blink of an eye, arriving at our radio telescopes from across the observable universe. Fast radio bursts were first discovered not in real time, but in archived data. In 2007, a graduate student named David Narkovich, working with astronomer Duncan Lorimer, was searching through archival recordings from the Parkes Observatory radio telescope in Australia, looking for dispersed radio pulses in data collected years earlier. He found one, a single intense pulse that had swept across the radio band in a characteristic way, lower frequencies arriving slightly later than higher frequencies, the signature of radio waves traveling through the ionized gas of intergalactic space. That sweep, called dispersion, is not just a peculiarity. It is a tool. The amount of dispersion tells astronomers how much ionized material the burst passed through on its journey, which in turn tells them approximately how far it traveled. The burst Lorimer and Narkovich found had traveled an enormous distance, from a source billions of light years away. The first fast radio burst had been discovered in data that was already several years old. The discovery was important, but puzzling. A single event tells you very little. Was it a one-time catastrophic event? The collision of two neutron stars, the final evaporation of a primordial black hole, the destruction of a cosmic string? Or was it something repeating, a persistent source that would produce bursts again? The answer came in 2012, when the first repeating fast radio burst was discovered. FRB 121 102, later localized to a dwarf galaxy approximately 3 billion light-years from Earth, produced bursts again and again, ruling out any explanation involving a one-time catastrophic destruction of its source. Something in that distant galaxy was producing bursts repeatedly over years of observation. But not all fast radio bursts repeat. Some appear only once, despite extensive follow-up monitoring. This may mean there are genuinely different types of fast radio burst, different physical processes producing signals that look similar. Or it may mean that all fast radio bursts repeat, but most sources repeat too infrequently for us to have observed them doing so. The rate of detection has increased dramatically as more sensitive instruments have come online. The CHIME telescope in British Columbia, a radio telescope optimized specifically for detecting fast radio bursts, now detects approximately 100 bursts per day. The sample has grown from a handful of events to thousands. The leading explanation for at least some fast radio bursts involves magnetars, neutron stars with extraordinarily powerful magnetic fields. A magnetar in our own galaxy, SGR 1935+2154, produced a fast radio burst-like event in 2020, providing the first direct observational link between magnetars and fast radio bursts. The event was less energetic than cosmological fast radio bursts, but its characteristics were consistent with the magnetar explanation. One reason the magnetar explanation is attractive is that magnetars are known to produce intense flares. Their magnetic fields can rearrange suddenly, releasing enormous amounts of energy. A particularly powerful magnetar flare might produce a fast radio burst visible from billions of light-years away. But no single model explains all the properties of all observed fast radio bursts. The diversity of burst properties, different durations, different frequency structures, different repetition rates, suggests that either fast radio bursts have multiple origins, or that the magnetar model needs significant development. Scientists have found that fast radio bursts are useful as cosmological probes quite apart from the mystery of their origin. As a burst travels from its distant source to our telescopes, it passes through the ionized gas of the intergalactic medium, the thin plasma filling the vast spaces between galaxies. This passage imprints information on the burst. The dispersion measure encodes the density of ionized material along the line of sight. By studying the dispersion measures of many fast radio bursts and comparing them to independent estimates of distance, astronomers are using fast radio bursts to map the distribution of ionized matter in the universe, including matter that cannot be detected any other way. Researchers believe that the mystery of fast radio bursts will eventually yield to sustained observational effort as the sample grows and individual sources are studied in greater detail. But for now, they remain among the most energetic and least explained phenomena in the observable universe. Brief flashes from the depths of space, carrying enormous power, and, for the moment, an unresolved story. The universe produces signals that we struggle to interpret. But there is another mystery of cosmic silence, an absence of signal that may be just as profound as any signal we have received. That absence is where we are going next. The Milky Way galaxy contains somewhere between 100 billion and 400 billion stars. The universe contains approximately 2 trillion galaxies. The total number of stars in the observable universe is estimated at approximately 10 to the power of 24, a 1 followed by 24 zeros, a number so large it exceeds any intuitive comparison. Many of these stars have planets. Astronomers have confirmed thousands of exoplanets, planets orbiting other stars, and statistical analyses suggest that most stars have planetary systems. Many of these planets are in the habitable zones of their stars, at distances where liquid water could exist on the surface. Given these numbers, the question seems almost inevitable. Where is everyone? This is the Fermi paradox, named for the Italian-American physicist Enrico Fermi, who reportedly raised it during a lunch conversation with colleagues at Los Alamos in 1950. The conversation was about flying saucers and other things, and at some point, Fermi asked simply, "But where are they?" The question has a deceptive simplicity. If the universe contains so many stars and so many planets, and if life arose on at least one of them, our own, then the statistical expectation is that life should have arisen on many others. And if life can give rise to intelligent civilizations, as it did here, then the statistical expectation is that some of those civilizations should be older than ours by millions or billions of years. And in millions or billions of years, a civilization with access to the physics we know could expand across a significant fraction of the galaxy. And yet, no confirmed detection of any extraterrestrial signal, no artifact, no visitor. The universe appears, from our vantage point, to be silent. In 1961, the astronomer Frank Drake formalized the question with an equation. The Drake equation estimates the number of communicating civilizations in the Milky Way by multiplying together a series of factors: the rate of star formation, the fraction of stars with planets, the fraction of those planets with life, the fraction where life develops intelligence, the fraction that develop communicating technology, and the average length of time such a civilization communicates. Most of the early factors in the Drake equation are now reasonably well constrained by observation. We know approximately how fast stars form. We know from exoplanet surveys that planets are common, but the later factors, the fraction of planets that develop life, the fraction of life that becomes intelligent, the average lifetime of a communicating civilization, are entirely unknown. The Drake equation, taken seriously, reveals not a calculation, but a list of our ignorances. The search for extraterrestrial intelligence, SETI, has been listening to the radio sky for artificial signals since 1960, when Frank Drake conducted Project Ozma, pointing a radio telescope at 2 nearby sun-like stars for a total of approximately 200 hours. In the decades since, SETI surveys have expanded enormously in scope and sensitivity. No confirmed artificial signal has been detected. The closest thing to an anomaly is the WOW signal, a narrow-band radio signal detected on the night of August 15, 1977, by Jerry Ehman using the Big Ear radio telescope at Ohio State University. The signal matched the profile of what an artificial extraterrestrial transmission might look like: narrowband, near the hydrogen line frequency of approximately 1,420 megahertz, and was approximately 30 times stronger than the background noise. Ehman circled the sequence of numbers and letters on the computer printout that represented the signal and wrote "wow" in the margin. The signal lasted 72 seconds, the length of time the telescope's rotating beam swept across the source position. It was never detected again. Decades of follow-up observations, including dedicated pointing of the Arecibo telescope, have found nothing at that position. In 2020, a team proposed that the signal came from a hydrogen cloud associated with a comet, but this explanation has been disputed. The WOW signal remains unexplained. There are many proposed resolutions to the Fermi paradox. Life may be extraordinarily rare. The emergence of life from chemistry may require conditions so improbable that it has happened only once or a handful of times in the observable universe. Intelligence may be rare. Life is common, but complex intelligent life is a rare development. Civilizations may destroy themselves through war, environmental collapse, or the development of technologies they cannot safely manage before achieving spacefaring capability. Communication may be different from what we expect. Civilizations may use methods of communication we have not yet thought to look for. The Great Filter Hypothesis, proposed by economist Robin Hanson in 1998, frames the paradox in terms of a barrier that civilizations face. Somewhere in the progression from simple chemistry to spacefaring civilization, there is something, some event or condition, that very few civilizations pass through. The Great Filter may be behind us, perhaps the emergence of complex multicellular life or of intelligence is extremely rare, or it may be ahead of us. A challenge that almost every advanced civilization fails to navigate. The implications of where the filter is are significant. If it is behind us, if the emergence of life or intelligence is the rare step, then our existence suggests we may have already passed the hardest barrier, and the future may be open. If it is ahead of us, if advanced civilizations routinely destroy themselves or are destroyed, then the silence of the universe carries a more sobering message. The silence of the universe is itself a data point. An absence of evidence is not evidence of absence, but it is information. The fact that we have searched for 70 years with increasing sensitivity and found nothing constrains the possible prevalence of advanced civilizations. Something is limiting the number of civilizations producing detectable signals, and what that something is remains one of science's most profound open questions. The universe's silence on the question of extraterrestrial intelligence is one kind of mystery. The universe has also produced, closer to home, a tension in the very numbers that describe its expansion, a disagreement that has grown more troubling the more carefully it has been measured. That tension is where we are going next. In 1929, Edwin Hubble published a paper that changed our understanding of the universe. By measuring the distances to galaxies and comparing them to their recession velocities, the speeds at which they were moving away from us, he established that more distant galaxies recede faster. The universe is expanding. The constant of proportionality in this relationship, the ratio of recession velocity to distance, is called the Hubble constant, denoted h0. It is one of the most fundamental numbers in cosmology, describing the current expansion rate of the universe and allowing astronomers to estimate cosmic distances and ages. For decades, measuring the Hubble constant accurately was one of the central challenges of observational cosmology. Hubble's original estimate was dramatically too high, approximately 500 kilometers per second per megaparsec, because of errors in the calibration of the distance scale that took decades to identify. Subsequent refinements brought the value down, and by the early 2000s, a consensus was emerging around a value in the vicinity of 70 kilometers per second per megaparsec. Then two things happened that complicated this picture considerably. The first was the Planck satellite's precise mapping of the cosmic microwave background, completed between 2009 and 2013. The pattern of temperature fluctuations in the CMB encodes a vast amount of information about the early universe, including, indirectly, the Hubble constant. By fitting the standard cosmological model to the Planck data, the Hubble constant can be inferred from first principles, from the physics of the universe at 380,000 years of age. The Planck collaboration obtained a value of approximately 67.4 kilometers per second per megaparsec. The second was increasingly precise measurements of the Hubble constant using the traditional cosmic distance ladder, a chain of distance measurements that begins with parallax measurements of nearby stars, extends to Cepheid variable stars, whose distance can be inferred from their pulsation periods, and reaches to Type 1a supernovae, stellar explosions of known intrinsic brightness, visible at cosmological distances. This approach measures the universe's expansion rate directly, using objects in the late universe. The result, from teams including the one led by Adam Rees, one of the discoverers of dark energy, is approximately 73 kilometers per second per megaparsec. The discrepancy between 67.4 and 73 is approximately 9%. In a field where the goal is precision at the 1% level, 9% is enormous, and the discrepancy has not gone away. As both measurements have been refined and improved, the tension has remained, growing, if anything, more statistically significant rather than less. It has crossed the threshold of 5 sigma, meaning it is extremely unlikely to be a statistical fluke. Something is genuinely different about what the two methods are finding. This is the Hubble tension, and it is one of the most discussed problems in modern cosmology. One possibility is that one or both measurements contains a systematic error, a subtle bias that has evaded detection despite careful analysis. The distance ladder measurement requires a chain of calibrations that could contain errors that compound. The CMB measurement relies on assuming the standard cosmological model is correct, an assumption that might not hold. Both possibilities are being actively investigated, but another possibility is more interesting. The Hubble tension may be telling us that the standard cosmological model is incomplete, that there is new physics operating in the early or late universe that changes the relationship between the CMB's features and the current expansion rate. Proposed resolutions involving new physics include early dark energy, a brief period in the early universe when an additional dark energy component altered the sound horizon. The scale of acoustic oscillations imprinted in the CMB that cosmologists use as a ruler. If the sound horizon was smaller than the standard model predicts, the inferred Hubble constant from the CMB would be larger, closer to the distance ladder value. Other proposals involve additional light particles in the early universe, modifications to gravity, or new forms of dark matter. None of these proposals has been confirmed. Each makes specific predictions that future observations can test. The Vera C. Rubin Observatory, the legacy survey of space and time, is expected to measure cosmological distances with unprecedented precision by detecting millions of supernovae and other distance indicators. The Euclid Space Telescope is mapping the large-scale structure of the universe with great accuracy. Future CMB experiments are planned with even finer angular resolution than Planck. These observations will either reveal a systematic error in one of the measurements, resolving the tension, or they will confirm it, making the case for new physics beyond the standard model even more compelling. Researchers believe the Hubble tension may be one of the most important clues available to cosmology about physics beyond our current understanding. A 9% discrepancy between two independently measured quantities that should agree is not a small thing. It is the kind of discrepancy that, in the history of physics, has sometimes pointed toward fundamental new discoveries. What the universe's expansion rate is exactly remains an open question, and its resolution may illuminate not just the value of a number, but the nature of the universe itself. There is another mystery in the universe that involves particles of almost incomprehensible energy arriving from unknown sources. That mystery is where we are going next. Instead, he found the opposite. As he ascended, radiation levels increased. By the time he reached 5,000 meters, radiation was several times stronger than at the surface. Whatever was producing it was coming not from below, but from above, from space. Hess had discovered cosmic rays. The discovery earned him the Nobel Prize in Physics in 1936. Cosmic rays are not, despite the name, rays in the sense of electromagnetic radiation. They are primarily high-energy particles, protons and atomic nuclei, occasionally electrons and gamma rays, arriving from space with a broad range of energies. At the lower end, they arrive from the Sun and from relatively nearby sources in our galaxy. At the higher end, they arrive from far beyond our galaxy, from sources that have accelerated them to energies far exceeding what any human-built particle accelerator can achieve. The highest energy cosmic rays, the ultra-high energy cosmic rays, are particles with energies exceeding 10 to the power of 20 electron volts. To put this in perspective, the Large Hadron Collider at CERN, the most powerful particle accelerator ever built, reaches energies of approximately 10 to the power of 13 electron volts. Ultra-high energy cosmic rays are 10 million times more energetic than the LHC's maximum output. They are the most energetic particles ever detected, and their sources are not definitively known. In 1991, an event was detected by the Fly's Eye detector in Utah that has become a landmark in particle astrophysics. The Oh My God particle. It was a cosmic ray proton with an energy of approximately 3 times 10 to the power of 20 electron volts. The kinetic energy of a single proton moving at that speed is comparable to the kinetic energy of a baseball pitched at 100 kilometers per hour. A macroscopic amount of energy concentrated in a particle 1 billion times smaller than an atom. The oh my god particle remains one of the most extraordinary events ever detected in physics. The mystery deepens because of a theoretical constraint called the GZK limit, proposed in 1966 by Kenneth Greisen, Georgy Zatsepin, and Vadim Kuzmin. Cosmic rays above a certain energy, approximately 5 times 10 to the power of 19 electron volts, should interact with the photons of the cosmic microwave background during their journey through intergalactic space, losing energy with each interaction. Above this energy, cosmic rays should not be able to travel more than about 160 million light-years without losing too much energy to be detected at ultra-high energies. Yet ultra-high energy events are detected. This implies that their sources must be relatively nearby, within roughly 100 to 200 million light-years. But identifying those sources has proven difficult. The magnetic fields of our galaxy and of intergalactic space deflect charged particles, scrambling the directional information that would allow us to trace cosmic rays back to their sources. The Pierre Auger Observatory in Argentina, covering an area of approximately 3,000 square kilometers on the Argentinian Pampas, is the world's largest cosmic ray detector. It uses 2 complementary detection methods: an array of 1,600 water tanks that detect the shower of secondary particles produced when a cosmic ray strikes the upper atmosphere, and fluorescence telescopes that detect the ultraviolet glow of the air shower as it propagates through the atmosphere. Together, these methods allow the energy, direction, and composition of incoming cosmic rays to be reconstructed. The telescope array in Utah has detected a concentration, a hotspot, of ultra-high energy cosmic rays arriving from one region of the sky, suggesting a nearby source. Possible sources include the radio galaxy Centaurus A and the Virgo cluster, both within the GZK distance limit. But no source has been definitively identified. Interestingly, cosmic ray research has contributed significantly to particle physics beyond its own mysteries. Before particle accelerators could reach sufficiently high energies, cosmic rays were the primary tool for discovering new particles. The positron was discovered in cosmic rays in 1932. The muon was discovered in cosmic rays in 1936. Pions were discovered in cosmic rays in 1947. The cosmic ray beam, entirely uncontrollable and arriving from unknown sources, served as the particle physics laboratory of the mid-20th century. Today, the highest energy cosmic rays take this tradition to its extreme. They carry energies that no laboratory will be able to match in the foreseeable future. Whatever is producing them, whatever object or process in the universe is capable of accelerating particles to energies 10 million times higher than the LHC, is doing something that physics would very much like to understand. The sources of ultra-high energy cosmic rays remain unknown. Their detection is certain. They arrive, they produce their enormous air showers, they are measured and recorded. But the cosmic accelerators that produce them, the objects in the universe capable of such extraordinary energetics, have not been definitively identified. The universe is producing phenomena that exceed our current understanding of what is physically possible. This is perhaps most acutely felt in the realm of theoretical physics itself, where the two most successful theories ever developed refuse to be reconciled with each other. That incompatibility is where we are going next. General relativity. Einstein's 1915 theory of gravity describes gravity not as a force, but as the curvature of space-time caused by mass and energy. It has been tested with extraordinary precision. It correctly predicts the precession of Mercury's orbit, the bending of light by the sun's gravity, the gravitational redshift of light climbing out of a gravitational well, and the existence and properties of gravitational waves. Every test conducted in over a century has confirmed it. Quantum mechanics, developed in the 1920s by Heisenberg, Schrödinger, Dirac, and others, describes the behavior of matter and energy at the smallest scales. It underlies all of chemistry, all of electronics, all of materials science. It correctly predicts the behavior of atoms, molecules, semiconductors, and laser light. It has been tested to extraordinary precision. The anomalous magnetic moment of the electron agrees with quantum mechanical predictions to 1 part in a trillion. No physical theory has ever been more precisely confirmed. And yet, when you try to apply both theories to the same physical situation, to the singularity at the center of a black hole, or to the moment of the Big Bang, or to space-time at the smallest possible scales, they give contradictory answers. Mathematical infinities arise that cannot be removed by the standard techniques of quantum field theory. The two theories, each impeccably accurate in its own domain, refuse to fit together. This is the quantum gravity problem, and it has resisted solution for nearly a century. The scale at which both theories would need to apply simultaneously is called the Planck scale, named for Max Planck, who first identified its significance. The Planck length, approximately 10 to the negative 35 meters, is 16 orders of magnitude smaller than the scale probed by the largest particle accelerator ever built. The Planck energy, the energy density at which quantum gravitational effects become significant, is approximately 10 to the 19th times the mass of a proton in energy units. These numbers are so extreme that no foreseeable technology can probe the Planck scale directly. The quantum gravity problem is not merely theoretically challenging. It is experimentally inaccessible by any current or near-future means. Two major candidate theories have been developed to address the problem. String theory proposes that the fundamental entities of physics are not point-like particles, but tiny one-dimensional vibrating strings. Different modes of vibration correspond to different particles, and one particular vibrational mode corresponds to the graviton, the hypothetical carrier of the gravitational force. String theory naturally incorporates gravity alongside the other forces of nature, but it requires the existence of extra spatial dimensions, 6 or 7 beyond the 3 we experience, compactified at the Planck scale, and therefore undetectable with current technology. String theory has produced an enormous number of consistent vacuum states, perhaps 10 to the 500, each corresponding to a different universe with different physical laws, and it has not yet produced a confirmed experimental prediction. Loop quantum gravity takes a different approach. Rather than starting from particle physics and adding gravity, it starts from general relativity and attempts to quantize space-time itself. In loop quantum gravity, space is not continuous, but is made of discrete quantum chunks, loops of quantum geometry, at the Planck scale. The theory does not require extra dimensions, but it has also not yet produced confirmed experimental predictions distinguishable from those of general relativity. One deeply interesting implication of attempts to develop quantum gravity is the question of time. In quantum mechanics and classical mechanics, time is an external parameter, a background on which physical processes evolve. In general relativity, time is part of the fabric of space-time, which itself is dynamical. When you try to combine the two, when you write down the equation that should describe quantum gravity, time disappears. The Wheeler-DeWitt equation, one candidate for a quantum gravity equation, contains no time variable at all. Some physicists take this seriously and propose that time is not a fundamental feature of the universe, but an emergent phenomenon arising from more fundamental quantum relationships. If time is emergent, then the questions of what happened before the Big Bang and what time really is take on a different character. The questions themselves may be based on an assumption about time that breaks down at the fundamental level. Quantum entanglement also has intriguing connections to quantum gravity. The ER equals EPR conjecture, proposed by Juan Maldacena and Leonard Susskind in 2013, suggests that quantum entanglement and wormholes, tunnels through space-time, are related phenomena. Two entangled particles may be connected by a microscopic wormhole. If correct, this would suggest that the structure of space-time itself is built from quantum entanglement, a deep connection between the two seemingly irreconcilable theories. These ideas are speculative but mathematically precise. They are not vague philosophical suggestions, but rigorous proposals that make specific mathematical claims. Whether they are correct remains to be seen. The quantum gravity problem is not merely an abstract puzzle. It blocks progress on virtually every deep question in cosmology: the nature of the Big Bang singularity, the interior of black holes, the ultimate fate of Hawking radiation. Until it is solved, there is a fundamental limit to how deeply we can understand the universe. The universe, at its smallest and its largest scales, is connected by mysteries we cannot yet bridge. And some of those mysteries manifest as structures in the universe that our models struggle to explain. Those structures are where we are going next. The universe on the largest scales is supposed to be boring. This is not an insult. It is a technical statement. The cosmological principle, one of the foundational assumptions of modern cosmology, holds that the universe is homogeneous and isotropic on sufficiently large scales. Homogeneous means the same everywhere. No special locations, no privileged regions. Isotropic means the same in all directions. No preferred axis, no special direction to look. On scales larger than roughly 300 million light-years, the cosmological principle predicts that the universe should be smooth, matter distributed uniformly, with no individual structures larger than that scale. Individual galaxies and galaxy clusters and even superclusters can exist, of course. On smaller scales, the universe is lumpy and structured. But beyond the scale of superclusters, the cosmological principle says the universe should look the same in all directions and from all locations. Several observations have found structures that appear to challenge this assumption. The Hercules Corona Borealis Great Wall was identified in 2013 using gamma-ray burst data. Gamma-ray bursts, extraordinarily energetic explosions, are visible across cosmological distances, and they trace the locations of massive stars and star-forming regions. The distribution of gamma-ray bursts showed an excess in one region of the sky, a concentration suggesting a structure of enormous size. The estimated scale of this structure is approximately 10 billion light-years. 10 billion light-years. The observable universe is approximately 93 billion light-years across. A single structure spanning 10 billion light-years would be more than 10% of the observable universe's diameter, vastly larger than the scale at which the cosmological principle says structures should not exist. Whether the Hercules Corona Borealis Great Wall is a real coherent structure or a statistical artifact of the gamma-ray burst distribution is debated, but its apparent scale has contributed to a growing literature suggesting that the cosmological principle may need re-examination. The Boötes void is a different kind of anomaly. Not too much matter in one place, but too little. Discovered in 1981 by Robert Kirshner and colleagues during a redshift survey, the Boötes void spans approximately 330 million light-years in diameter. Within it, the density of galaxies is dramatically lower than in the surrounding universe. Only approximately 60 galaxies are known inside it, where several hundred would be expected if the surrounding density continued uniformly. Large voids are expected in the cosmological model. The cosmic web of filaments and clusters is surrounded by such voids. But the Boötes void is unusually large and unusually empty by any standard. Its origin remains a subject of discussion. The Great Attractor is perhaps the most evocative of these anomalies, a gravitational influence so large that our galaxy and thousands of others are falling toward it at approximately 600 kilometers per second. The Great Attractor was identified in the 1970s and 1980s by studying the peculiar velocities of galaxies, the components of their motion that deviate from the simple Hubble flow of the expanding universe. A coherent motion of thousands of galaxies toward a single region of space implies an enormous concentration of mass in that direction. The concentration, centered approximately 250 million light-years away in the direction of the Centaurus constellation, was named the Great Attractor. What makes studying the Great Attractor difficult is its location. It lies in the direction of the galactic plane, the disk of the Milky Way, which is filled with dust and gas that absorbs and scatters the light from more distant objects. X-ray and radio observations can penetrate this obscuring medium, and they have revealed the Norma cluster and other galaxy clusters in the region. The Great Attractor appears to be a supercluster of galaxies, but whether it fully accounts for the observed gravitational pull, or whether there are additional concentrations of mass beyond it, is still being worked out. Closer to home, the Milky Way itself has structures that have required explanation. The Fermi bubbles, discovered in 2010 using the Fermi Gamma Ray Space Telescope, are two enormous lobes of hot plasma extending approximately 25,000 light-years above and below the galactic plane. They are symmetric about the galactic center, extending on both sides like a vast figure 8. The energy required to produce them is comparable to 1 million supernova explosions. Their origin is debated. One proposal is that they were produced by a past period of intense star formation near the galactic center. The collective winds and supernova explosions of many massive stars driving plasma out above and below the galactic plane over millions of years. Another proposal is that they were produced by a past period of active accretion by Sagittarius A star, the central black hole consuming material at rates far higher than today, with jets or winds driving plasma out along the rotation axis of the galaxy. Both explanations are plausible. Neither is definitively confirmed. One other anomaly is worth mentioning. Several galaxies have been discovered in the past decade that appear to contain very little dark matter, a finding that challenges the standard model of galaxy formation, in which dark matter is the scaffolding that first collapses under gravity and allows ordinary matter to accumulate into galaxies. If some galaxies have formed without dark matter, the story of galaxy formation may be more complex than currently understood. The universe, it turns out, does not always behave exactly as our models predict. The anomalies accumulate quietly, each one individually perhaps explicable, but collectively suggesting that our picture of the large-scale universe may be missing something important. The universe has also sent us signals that resist explanation. Signals whose nature we have studied for decades without arriving at a fully satisfying answer. Those signals are where we are going next. On the evening of August 15th, 1977, a radio telescope called Big Ear at Ohio State University was scanning the sky, recording radio signals from space onto a computer printout. Big Ear was participating in SETI, the search for extraterrestrial intelligence, listening for narrowband radio signals that might indicate a technological origin. When astronomer Jerry Ehman reviewed the printout a few days later, he found something extraordinary. In the data was a sequence of numbers and letters representing signal strength, 6EQUJ5. In the encoding system used by Big Ear, letters represented signal strengths above 9, so the sequence indicated a signal that rose from a strength of 6 to a peak corresponding to the letter U, more than 30 times the background noise level, and then fell away. The signal had lasted exactly 72 seconds, the length of time it took Big Ear's fixed beam to sweep across a point source as the Earth's rotation carried the telescope past it. Ehman circled the sequence and wrote "Wow" in the margin. The signal had characteristics that were, in some respects, consistent with what an artificial extraterrestrial signal might look like. It was narrowband, concentrated in a very small range of frequencies, rather than the broadband hiss of natural radio sources. It was centered near 1,420 megahertz, the frequency at which neutral hydrogen emits and absorbs radiation, a frequency that has been proposed as a natural channel for interstellar communication because hydrogen is the most abundant element in the universe, and any technological civilization would know its frequency. What the signal was not was repeatable. despite extensive follow-up observations, including dedicated pointing of the Arecibo telescope at the source position. The signal was never detected again. The sky at that location has been observed many times since. Nothing comparable has been found. Various natural explanations have been proposed and examined. Satellites and terrestrial interference were ruled out by the geometry of the observation. A 2020 paper proposed that the signal came from a hydrogen cloud associated with a comet passing through the field of view. Comets can emit radio waves near the hydrogen line as water molecules are broken apart by sunlight. But this explanation has been disputed by other researchers, and the question of the WL signal's origin remains genuinely open. The universe produces other signals that resist complete explanation. Sagittarius, a star, the supermassive black hole at the center of the Milky Way, is normally a relatively modest source of X-ray emission, but it produces flares, sudden increases in X-ray brightness by factors of hundreds to thousands, lasting for hours. These flares are monitored regularly by X-ray telescopes in orbit, and they remain incompletely understood. Possible mechanisms include the tidal disruption of asteroids or comets that wander too close to the black hole, magnetic reconnection events in the hot plasma near the event horizon, and instabilities in the disk of material orbiting the black hole. The precise trigger and mechanism of these flares are not established. Pulsars, the rapidly rotating neutron stars that emit beams of radio waves, were themselves mysterious signals when first discovered. In 1967, Jocelyn Bell Burnell, a graduate student working with Anthony Hewish at the University of Cambridge, noticed a repeating radio signal in the data from a new radio telescope, a pulse arriving every 1.337 seconds with extraordinary regularity. The regularity was so remarkable, so much more precise than any known natural radio source, that for a period, the signal was designated LGM1, Little Green Men 1. The designation was partly tongue-in-cheek, but it reflected a genuine moment of uncertainty about whether the signal might be artificial. Pulsars were eventually understood as rapidly rotating neutron stars, the collapsed remnants of massive stars, spinning many times per second and emitting beams of radio waves that sweep across space like cosmic lighthouses. Their nature explained. But the initial uncertainty about an unexplained repeating signal from space is worth remembering. A reminder of how difficult it can be to interpret a new kind of signal when no framework for understanding it yet exists. In 2023, multiple pulsar timing array collaborations, including Nanograv in North America, the European Pulsar Timing Array, and others, announced the detection of a gravitational wave background. Pulsar timing arrays use networks of millisecond pulsars, the most stable natural clocks in the universe, as a galactic-scale gravitational wave detector. Gravitational waves passing through the galaxy cause tiny, systematic variations in the arrival times of pulsar pulses. By monitoring dozens of pulsars for years and looking for correlated variations consistent with gravitational waves, the collaborations detected a background hum, a sea of gravitational waves permeating the universe. The most likely source is the population of supermassive black hole binaries throughout the universe. pairs of supermassive black holes in galaxies that have merged, slowly spiraling together and emitting gravitational waves. The signal is consistent with this interpretation, but it could also contain contributions from other sources: cosmic strings, phase transitions in the early universe, or other exotic phenomena. The detailed analysis of the gravitational wave background and what it reveals about the population of supermassive black holes is ongoing. The universe is, in every direction, producing phenomena that we have not yet fully decoded. Each signal is a message. Some we can read, some we have deciphered only recently, and some, like the wow signal, remain, after decades, unanswered. There is a final category of mystery that does not involve any specific observation or signal, but touches the most fundamental question of all: why the universe is the way it is, rather than any other way. That is where we are going next. The universe runs on numbers. Not just any numbers, specific values of fundamental constants that appear in the equations of physics: the strength of gravity, the mass of the electron, the speed of light, the charge of a proton, the cosmological constant, the strength of the strong nuclear force. These constants are not derived from any deeper theory. They are measured experimentally and inserted into equations as given facts of nature. They are the universe's operating parameters, and everything that exists depends on their precise values. What makes these parameters remarkable? What makes them, in the language of physics, fine-tuned, is that small changes in their values would produce a universe radically different from ours. A universe, in most cases, incompatible with the existence of complex matter, stars, planets, or life of any kind. Consider gravity. If gravity were significantly stronger than it is, stars would form from smaller amounts of gas, burn hotter and faster, and exhaust their fuel in thousands of years rather than billions. Too short a time for planetary systems to develop the complex chemistry necessary for life. If gravity were significantly weaker, gas clouds would never collapse into stars at all, and the universe would remain a diffuse soup of hydrogen and helium without any gravitational structures. Consider the cosmological constant, the parameter associated with dark energy. The observed value of the cosmological constant is extraordinarily small, almost but not quite zero. If it was somewhat larger, if dark energy was somewhat stronger, the universe would have expanded so rapidly in its early history that gravity could never have assembled matter into galaxies. Stars would not have formed. The universe would be a thin, cold, rapidly expanding soup of particles. If the cosmological constant were negative, corresponding to a contracting force, the universe would have collapsed long before stars and planets could form. The observed value appears to sit in a narrow window, compatible with structure formation. This is remarkable, but what makes it even more remarkable is the cosmological constant problem, one of the greatest discrepancies in the history of physics. Quantum field theory, the framework underlying the standard model of particle physics, predicts that empty space should have an energy density arising from quantum fluctuations. The calculation of this vacuum energy gives a value approximately 10 to the power of 120 times larger than the observed value of the cosmological constant. This is the largest discrepancy between theoretical prediction and observation in all of physics. A mismatch of 120 orders of magnitude. Some unknown mechanism, is cancelling the enormous predicted vacuum energy to extraordinary precision, leaving a tiny residual that corresponds to the observed dark energy. What that mechanism is, nobody knows. The strong nuclear force presents another example. If it were slightly weaker, protons and neutrons would not bind into atomic nuclei. No nuclei, no atoms beyond hydrogen, no chemistry, no molecules, no life. If it were significantly stronger, all hydrogen would have fused into helium and heavier elements in the Big Bang, leaving no hydrogen for water or for stellar fuel. Astronomer Fred Hoyle predicted in 1953, using anthropic reasoning, that carbon must have a specific energy level in its nucleus for stellar nucleosynthesis to produce the carbon that living things are made of. Without the Hoyle state, as this energy level became known, the nuclear processes in stars would produce almost no carbon. The Hoyle state exists at precisely the energy Hoyle predicted. These examples, and there are many others, constitute the fine-tuning problem. The fundamental constants of nature appear to be set to values that permit complexity, and small changes in many of them would produce a universe incompatible with anything resembling our own. Two broad classes of explanation have been proposed. The first is the anthropic principle, the observation that any observer capable of noting the values of the constants must be in a universe whose constants are compatible with observers. This is a selection effect. We could not be in a universe where the constants were incompatible with life, because such a universe would not contain us to observe it. The anthropic principle does not explain why the constants have the values they do. It explains only why we would find ourselves in a universe with life-compatible constants, whatever fraction of possible universes those might be. The second is the multiverse, the proposal that a vast number of universes exist, each with different values of the fundamental constants. In a multiverse of sufficient size and diversity, some universes will, by chance, have constants compatible with complex matter and life. We find ourselves in one of those because we could not be in any other. The multiverse transforms the fine-tuning from a mysterious coincidence into a selection effect across an ensemble of universes. The multiverse has a serious problem as a scientific explanation. It is, in most of its versions, untestable. If other universes exist but are permanently causally disconnected from ours, if no signal or observation can ever reveal their existence, then the multiverse is not, in the strict sense, a scientific hypothesis. It is a philosophical one. Some physicists accept this and argue that it is nonetheless the most satisfying resolution to the fine-tuning problem. Others find the untestability disqualifying. There is a third possibility, that some deeper theory of physics, not yet discovered, will derive the values of the fundamental constants from first principles, showing that they could not be otherwise. This possibility has not been realized, and string theory, which generates an enormous landscape of possible vacuum states with different constants, has, if anything, made this prospect seem less likely rather than more. The fine-tuning mystery sits at the deepest level of our understanding of nature, at the boundary between physics and philosophy, between what science can address and what lies beyond its current reach. Why is the universe comprehensible at all? Why does mathematics describe nature so precisely, as the physicist Eugene Wigner once asked? Is perhaps the finest expression of this mystery. It is a question that leads not to an answer, but to a deeper appreciation of how extraordinary it is that the universe is the way it is. And that appreciation, that quiet sense of wonder at the universe's extraordinary character, is where we will rest as we bring tonight's journey to its close. That is where we are going next. The mysteries have been described. Dark matter and dark energy, the invisible 95% of the universe whose nature we do not know. The beginning, the Big Bang, the inflation that solved the horizon and flatness problems but raised questions of its own, and the singularity before which physics falls silent. The end, the heat death, or the Big Rip, the arrow of time that physics cannot explain, the vast future in which the universe expands into cold darkness, the black holes, the singularity where physics breaks down, the information paradox, the supermassive black holes that formed faster than our models can account for, the matter-antimatter asymmetry, the tiny imbalance that allowed everything to exist, the fast radio bursts, the brief intense pulses from across the universe whose sources are not fully explained, the Fermi paradox, the silence of the universe, and the wow signal that spoke once and never again, the Hubble tension, the 9% disagreement that may indicate physics we have not yet found, the ultra-high energy cosmic rays arriving from unknown accelerators with energies no human machine can approach, the quantum gravity problem, the two most successful theories in history, incompatible with each other, the great structures, the Hercules Corona Borealis Great Wall, and the Boötes Void and the Great Attractor that challenge our models of the cosmos, the fine-tuning mystery, the constants of nature set to values that permit us to exist without any known reason why. All of that is there now, somewhere in the mind, held gently, without any need to resolve it tonight. What remains is simply to rest in it. Every atom in your body, heavier than hydrogen, was forged inside a star. The carbon in your cells, the calcium in your bones, the iron in your blood, none of it was present in the early universe. It was synthesized in the nuclear furnaces of stars that lived and died before the sun was born, scattered into space by stellar winds and supernovae, gathered by gravity into the cloud of gas and dust from which the solar system formed, incorporated into the Earth, and eventually into you. You are made of the universe's history. The light you see on a clear night has been traveling toward you for years, for decades, for centuries, for thousands of years. The light from the Andromeda Galaxy, just visible to the naked eye as a faint smudge in the northern sky, left that galaxy approximately 2.5 million years ago, when our ancestors were just beginning to use stone tools. That light has been traveling through the universe for 2.5 million years to reach your eye on this evening. The cosmic microwave background, the afterglow of the Big Bang, is present everywhere right now. Every cubic centimeter of space, including the space around you, is filled with approximately 411 photons of CMB radiation, the oldest light in the universe, cooled by 13.8 billion years of cosmic expansion to a temperature of 2.7 degrees above absolute zero. It is faint and invisible to our eyes, but it is there, bathing everything in the universe in the remnant warmth of the beginning. The same laws of physics that govern the hydrogen in your body also govern the hydrogen in a galaxy 2 trillion galaxies away. The same quantum mechanics, the same electromagnetism, the same gravity. Across all the vast and ancient distances of the observable universe, the laws have been the same everywhere we have been able to test them. The universe speaks one language, even if we have not yet learned all of its vocabulary. The mysteries we have visited tonight are not signs of science's inadequacy. They are the frontier. They are where the questions have been asked carefully enough and the observations made precisely enough that the edges of our knowledge become visible. The Hubble tension exists because our instruments are precise enough to measure the expansion rate of the universe to a fraction of a percent. The fine-tuning mystery exists because we understand the equations of physics well enough to ask what happens when constants change. The information paradox exists because we understand quantum mechanics and general relativity well enough to see where they contradict each other. The questions are as extraordinary as the answers we have already found. And there is something worth noting about where we are in time. We live in an era when the evidence for the Big Bang is still observable, when the CMB is still detectable, when the large-scale structure of the universe still traces the imprint of the early cosmos, when the recession of galaxies still tells us the story of the expansion. In 2 trillion years, all of this evidence will be gone, carried over the cosmological horizon by the expansion of space. Future civilizations, if any exist, will look out on a static and apparently isolated island of stars, unable to discover what we know. We are fortunate to exist in the moment when the universe is still legible, when its history is written in the light of distant galaxies and the faint warmth of the CMB and the distribution of hydrogen across cosmic scales. We are the generation that first measured the expansion of the universe, first imaged a black hole, first detected gravitational waves. We have more questions than answers, but the questions are extraordinary ones. The universe is vast. It is ancient. It is mostly unknown. And it is, in some sense that resists easy articulation, extraordinarily beautiful. The dark matter moves silently through you right now, passing through your body without interacting, as it passes through the Earth and the Sun and the galaxy, a component of the universe we know exists but cannot see. The CMB photons drift through the room where you are resting, the coldest remnant of the hottest moment in history. Somewhere on the other side of the observable universe, a fast radio burst has just occurred, an event releasing the energy of thousands of years of stellar output in a millisecond, and its signal is traveling toward us at the speed of light and will reach our telescopes in billions of years when we are long gone. The universe is patient. Its mysteries are patient. They have been waiting for billions of years for someone to ask about them. They will wait as long as it takes for the answers. Sleep well.